Want to do another quick example with you guys here. This is one that they didn't give. You can think of this as a third definition besides elastic collisions where momentum and energy are conserved. We just watched a video on an inelastic collision where momentum was conserved but energy was not. And this is actually a third case called superelastic. In superelastic, once again, momentum is conserved, so that's easy. Momentum's always conserved. But energy is actually gained from some source. So we pick up energy somewhere. So let's say this is a situation. Let's say we got some frictionless ice. We've got a 1 kilogram block sitting there at rest and a 3 kilogram block, and we've got a compressed spring between them. That compressed spring holds elastic potential energy, and we can convert it into kinetic by letting it go. So boom, we let this explosion happen in a sense. An explosion can be thought of as a reverse collision. So boom, it explodes here. The 1 kilogram goes off to the left here. The 3 kilogram goes off to the right. Let's say that the 1 kilogram goes off at 12 meters per second. So first of all, let's find the velocity of the 3 kilogram. We're going to do that with conservation of momentum. So as always, the momentum before is equal to the momentum afterwards. Since everything's at rest before, we know that there's no momentum before. That means there has to be no momentum afterwards. But we do have two objects moving. Object 1 is moving and object 2 is moving. So their momenta must cancel out. They must be equal and opposite there. So let's solve for that here. Momentum of object 1 afterwards is going to be mass 1 times velocity 1 afterwards. And momentum of object 2 afterwards is going to be mass 2 times velocity 2 afterwards. So plugging in, mass 1 is 1 kilogram. Velocity 1 afterwards is negative 12 meters per second. That is very important. That means to the left. Mass 2 is 3 kilograms. And then we are solving for its velocity here. So 1 times negative 12 is negative 12. And if you do the algebra and solve for this, we know this has got to be, term has got to be 12 as well to cancel out with that negative 12. So what times 3 gives you 12? Velocity 2 must be 4 meters per second. You can actually almost do that in your head if you think about it logically. These two have to cancel their momentums out to get back to 0. This one's got 3 times the mass. So it must only have 1/3 the velocity of this one, so only 4 meters per second. So you could really do that quickly if you truly understand conservation of momentum. Don't get too equation dependent. Understand what we're doing with the equations, and you could have just easily done that one in your head. Let's look at the energy of this. So this is a superelastic collision. This one's actually kind of easy in terms of superelastic. The kinetic energy beforehand is going to be equal to 0 because nothing had velocity, and so there was no energy at all before. Let's find then the total energy afterwards. The total energy afterwards is going to equal the energy of object 1 afterwards and the energy of object 2 afterwards. So that's not very easy to see, is it? So let me right here in red, let's find the energy of object 1 afterwards. So that's going to be 1/2 times mass 1 times velocity 1 afterwards squared. And so its mass is 1, its velocity afterwards is 12. 12 squared is 244 times 1 times half of that is 122 joules of kinetic energy. By the way, it doesn't matter that it's negative 12. You could put that in there, but it gets squared, so it goes away. So I just never even put the negatives in. And then the kinetic energy of object 2 afterwards is 1/2 times its mass, which is 3, times its velocity, 4. Don't forget to square it. So 4 squared is 16. Half of 16 is 8. 8 times 3 is 24 joules. So the total amount of energy then afterwards is going to be the 122 joules from object 1 plus the 24 joules from object 2. So if you add that up, the total amount of energy afterwards is 146 joules. Where did that 146 joules come from? Does this violate conservation of energy? No, it was in the spring. The spring must have had 146 joules of elastic potential energy stored in it.